Hello, I'm Ramon Antonio. Let me present FastMosaic. Many core data types are naturally modeled by ND arrays. Array DBMSs operate on ND arrays and enable their storage, processing, and even visualization. You can learn more in the VLDB 2021 tutorial on array DBMSs. That tutorial is an in-depth survey accompanied by high-quality video lectures. The widely used Mosaic operator ingests a massive collection of overlapping arrays into a single large array, called Mosaic. For example, Oracle Spatial provides the respective procedure, ChronosDB has the Mosaic command, and Rastaman is equipped with the Mosaic recipe. The operator can utilize sophisticated statistical and machine learning techniques to produce a high-quality seamless mosaic. However, the performance bottleneck becomes a major challenge when applying such advanced techniques over increasingly growing array volumes. Earth remote sensing data constitute one of the most significant array DBMS workloads. Hence, consider a practical example related to real-world geospatial arrays, Landsat satellite scenes. Landsat is one of the most popular and the longest continuous space-based record of Earth's land. We prepared a set of 3x4 Landsat scenes, bands 1 through 7, and different dates. The scenes are 3D overlapping arrays representing an interesting agricultural area featuring central pivot irrigation fields in Saudi Arabia. This makes it possible to explore diverse conditions for the mosaicing algorithm. A single array, a satellite scene in this case, often doesn't fully cover the area of interest. In this case, the mosaic operator, equipped by data science techniques, is used to fuse a large collection of input arrays into a single seamless mosaic, a large multidimensional array where the visibility of stitches between individual input arrays is minimized. To produce high-quality mosaics, algorithms resort to advanced techniques like canonical correlation analysis. We introduce a new, scalable way to perform canonical correlation analysis that is orders of magnitude faster than the popular Python's scikit-learn library for the purpose of array mosaicing. Furthermore, we developed a hybrid web desktop application to showcase our novel FastMosaic operator based on this new, scalable canonical correlation analysis. For a pair of input arrays, reference and subject A and B respectively, we estimate the probability of no change for their overlapping cells using canonical correlation analysis. On the invariant cells, an orthogonal regression is built, whose k-pairs of coefficients are applied to all cells of the subject array. Two mosaicing modes are available, both resulting in a mosaic. The first is a manual mosaic plan, that is a batch run on all input arrays. And the second is a step-by-step detailed mode for two input arrays as shown on the slide. FastMosaic is implemented in Java, C#, Python, and JavaScript connected via a custom web server. Note that FastMosaic operates directly on ordinary files of standardized formats, GeoJSON, NetCDF, GeoTIFF, and others. So we can explore the mosaicing process in full depth at any stage. Let's go through the end-to-end workflow of constructing a seamless mosaic on raw input arrays using a graphical user interface. The application has several windows. The main window, guidelines window with instructions on how to use the application, console window, coefficients tool window, correlation plot tool. In addition, you see the empty folder to be used for storing the data during the work of the application. Regardless of the mosaicing mode, first we must define the mosaic plan using the Mosaic Plan tool. Let's launch it. As you can see, panning, zooming in and out, snapping, and full screen are supported. The user interactively builds a tree that is Mosaic Plan, or Mosaic Execution Plan, by drawing arrows to connect array paths and set the fusion order. In the batch mode at step number I, the array at the start of arrow I joins the mosaic build so far. Recall that our illustrative dataset consists of 3x4 Landsat scenes covering interesting agricultural areas in Saudi Arabia. Let me show you the geographical context. Here you see approximate footprints of the scenes. Let's refresh and connect two arrays, for example these two, as only two arrays are mosaicked in the detailed step-by-step mode. The subject array is at the beginning of the arrow, so we'll calculate transformation coefficients for this array. Now we're going to save the execution plan into GeoJSON to our working folder. So, okay, let's open it. Here how it looks like. It will be analyzed by the FastMosaic application to extract the fusion order. Next, we'll load our mosaic plan into the application. So working directory is set automatically to the location of the GeoJSON with the mosaic plan, but you can change it anytime in the main menu. So as you can see in the console, the plan consists of mosaicing two arrays. We are ready to create X and Y arrays with the sampling tool for the input of canonical correlation analysis. We just navigate to Tools, Sampling, to create a NetCDF file with the sampled cell values from overlapping cells of the two selected scenes. You will see a progress bar during the sampling operation. Success. Here it is. Let's launch a console for our working directory. And check its contents. So here we currently have our mosaic plan and the vector sample from the overlapping area. A quick look at the file with the command line tool reveals that we have, after filtering out node data cells, about 13 million in total, or almost 7 million vector pairs of length 7 in our sample for canonical correlation analysis. So let's close it. Next, the user sets the FastMosaic options to generate the map of no change probabilities and the regression coefficients. Option descriptions are in the paper, so we run FastMosaic with default options. During the CCA execution, the user can visually track the convergence of the algorithm with the interactive plot updated at each iteration step. In addition, the coefficients also appear in the console. Here, iterations are in progress, and you can investigate the convergence. Okay, great. Coefficients are calculated. As we have computed the p-node change array, here it is, we can generate the respective heat map to thoroughly inspect cells in the overlapping area that are likely invariant. Just run the heat map tool. So the heat map is generated. Here it is. Finally, we can build the mosaic. As we have only 2 input arrays for this detailed step-by-step mode, we have one set of normalization coefficients that are going to be applied to the subject array to generate a seamless mosaic. Let's run the mosaic tool. So it's being generated. Great, the mosaic is ready. Here it is. This is the resulting 3D array, so represented as a set of 2D arrays in GeoTIFF files. Well done. Now let's explore the data. You see the input arrays, that is 2 Landsat scenes from our mosaic execution plan. These are visualized in natural colors. It is apparent that the visual transition between the arrays is abrupt and looks like a stitch. However, a simple contrast tuning is not sufficient to fix this. It is a challenging task to build a high-quality mosaic. Here is how the heat map that we have just generated looks like. It is built for the overlapping area. It is 30% transparent, so underlying input arrays are also visible. Let's zoom in and have a more detailed look. Recall that it plots the no change probability for each cell. Finally, this is the resulting mosaic. Clearly, it is seamless as if it is a single array. It is amazing to compare it with the raw input. We can also zoom in such that we could be able to investigate the details. Here is the stitch that is present on the raw input, and here is the transformation of our raw data. So let's come back. So what is most important is that we can achieve this perfect results orders of magnitude faster compared to the state-of-the-art by using our novel, scalable canonical correlation analysis. Thank you for your attention.